as the question says, suppose the particle of the previous problem has a mass m and a speed v before the collision, and it sticks to the rod after the collision. The rod has a mass m, then find the velocity of the center of mass c of the system constituting the rod plus the particle b. Find the velocity of the particle with respect to c before the collision. C. Find the velocity of the rod with respect to c before the collision. Find the angular momentum of the particle and the rod about the center of mass c before the collision. Find the moment of inertia of the system about the collision. Find the velocity of the center of mass c and the angular velocity of the system about the center of mass after the collision. Proceeding with the first part, in which we need to find the velocity of center of mass. So conserving the momentum, since we are having the system of the rod and the particle, there is no external force. So conserving the linear momentum, we get mv equal to rod of mass rod plus particle into v dash, giving us v dash to be simply mv upon m plus v. Proceeding with the second part, in which we need to find out the velocity of the particle with respect to c before the collision. So it will be v minus v dash, right? So it will be v minus mv over m plus capital M, that is equals to mv over m plus n. Now friends, let us calculate the third part, in which we need to find the velocity of a rod with respect to c before the collision. Now we can write down that the velocity of rod with respect to the c before collision is minus times what its velocity is. So minus times mv upon m plus n, right? Coming to the d part, that is, find the angular momentum of the particle and the rod about the center of mass c before the collision. Now we all know that the center of mass distance is simply m1x1 in a two-particle system. It is m1x1 plus m2x2 upon m1 plus m2. So here we can write it as ml over twice of m plus m. And we all know that angular momentum is mvr. So here we can write it as m v, where v is mv over m plus m, and r being that we got from above, that is ml into 2m plus m, giving us the angular momentum of the body. So we are writing it as m body equals to m square m vl, giving upon 2 m plus m whole square. Now this is the linear momentum we got for the whole body. Now let us proceed to find, with the same concept, the angular momentum of the rod about center of mass. So it will be again mvr, but now the m is m, v being mv upon m plus n, and r being half of ml over m plus m, giving us mm square vl over twice of m plus m into whole square. Now how we got r over here was because r is now L by 2 minus ml by 2 into m plus n. So we got it as half m. This was small m actually. So half m plus n, right? Now proceeding to the E part of this question, in which we need to find the moment of inertia of the system about the collision, that is actually after the collision. Now we all know that the moment of inertia simply adds up, so we can write it as I1 plus I2, and so here we can write it as m r square, where r is capital M L 2 m plus m whole square plus ml square by 12 because it is at the about the center of mass plus capital M. Now this was the capital M because the mass of the rod was there, plus capital M into r square, that is ml over twice of m plus m whole square, giving us the moment of inertia to be capital M into capital M plus 4m L square upon 12 m plus m whole m plus m, not whole square actually, because, or will be getting it? No, the square won't be there because it will be cancelling out from above, because you will be getting a factor in the numerator also. Proceeding to the last part of this question, in which we need to find the velocity of the center of mass C and the angular velocity of the system about the center of mass after collision. Now we are having the velocity of center of mass to be mv upon m plus m. Yes, we are having I omega, that is the angular momentum, being mvr equals to mv into r, where r is ml over twice of m plus m, right? So simply we can write the omega to be 6 mv over m plus 4m into L. Now here we got this center of mass velocity from the A part only, because this was v dash, that is the when with respect to the center of mass only. So for center of mass we can write down the velocity to be this.